So, this is the third lecture of the combinatorics course. We were studying the pigeonhole principle. This is the third part of it. So, in the last class we considered some questions involving graphs. So, I somehow assumed that the student is comfortable with graph. Comfortable means he knows a little bit of graph theory, that I assume about almost everything. Like when I am talking about numbers, I am assuming that the student is to some extent familiar with the very basic notions, like any number can be decomposed into its prime factors, factorization, right, this like this, right, these kind of things, and divisibility. That means what does it mean to say that some number divides another number, what is the remainder, such things I am assuming. So, which will be the 12th standard level knowledge. For graph theory, so I am assuming that the students are familiar with what is a graph, what are vertices, what are edges, and the very basic notions like what is the degree of a vertex, and also that student have seen it before at least once. No in-depth knowledge is assumed, definitely. So, it is just some familiarity, basic familiarity. So, in case you are not already familiar with those concepts, what you can do is you can read the first chapter from any of the graph theory books available. So, it can be the book by Reinhard D. Stell, or it can be the book by Bondi and Murthy. And it can be the book by Harari. There are several books. You can or you can just search in the net, say go to Wikipedia and read something about graph theory. Even that would be enough, because we just need the basic things, and even those concepts like independent set, the coloring, I will remind, because if in the last class I introduced those notions, though I just did it fast, that is why I assume that you have seen it before. So, I am just reminding it. In case you do not understand it, you can go back and see it once again in one of those books or wherever you have studied, or otherwise you can see the NPTEL lecture on graph theory. That is, and in this course graph theory, though it is part of combinatorics, but it will not be taught in this course. So, if you want to study graph theory, you have to view the separate course on graph theory, but still things about graphs, ideas about graphs will keep coming in this course again and again, because here when we teach techniques to deal with combinatorial problems, to give examples we will have to take problems from graph theory, though it will be just to illustrate certain points most of the time, but because there are several nice examples that we can borrow from graph theory, we will be doing it time and again. Therefore, the student is supposed to know a little bit of it. Some basic familiarity is always assumed. And geometry also, when I talk of geometry, I will assume that the student knows the 12th standard level geometry and is familiar with most of the elementary concepts about Euclidean geometry. Even if he does not know, he can always search somewhere and find out the corresponding notions, but most of the, whenever something reasonably sophisticated comes, I will definitely explain. But of course, I can't keep on explaining what is a triangle, what is a rectangle and things like that, and also the area of triangle. Such notions I will definitely assume, and also the other notions, even from combinatorics, I will introduce the basic notions, but it will be very quick. So, whatever you have studied till 12th standard, you are supposed to revise a little bit before coming to this course. And of course, what are functions, what are relations, the things I may mention in passing, but not very carefully. So, in case you have difficulty, what you can do is you can read one of these books which I mentioned initially, this say Grimaldi and Ramana. Grimaldi is Grimaldi and Ramana's book, because the initial chapters contains all this required material. So, you can revise from those books. So, it's just a matter of when you do not understand something which I tell, you can just go to those chapters and quickly see what it is, the definition, if you just miss something. So, then you can keep, but it is quite difficult for me to remember that what all, like for when it comes to elementary notions, I may forget that this is not introduced, because it is so common and I mean very elementary that I may miss to introduce that. But in that case, you have to just look at some of those books. I mean those books will anyway contain all this material. So, because our plan is to soon get into more non-trivial things. So, we cannot spend too much time on this elementary notions. This is the plan. Now, again, so in the last class we dealt with two problems in graph theory. The first problem, remember, it was about the degrees of the vertices in a graph. Again, whenever I am talking about graph, I am assuming that the graphs are finite, right, finite, though I may not always tell it, finite and simple. When I say simple graph, it means we do not have self loops. So, for instance, not loops of this sort, right. So, these are not simple graphs, because these loops are there, and also I am assuming that there will not be things like this, right, multiple edges between two vertices, there is only one edge if at all. So, but in case if I am talking about multi-graphs, these are called multi-graphs, when we allow loops, self loops and multi edges, I will be mentioning that specifically, because it is more common to talk about finite and simple graphs than multi graphs. So, therefore, rather than always assuming that graph is a multi graph and then always saying that it is a finite simple graph, better we assume that whenever I say graph, I mean finite and simple graphs. That is, that will be our convention when we talk. So, and yeah, in the last class, the first problem was about the degrees. The second problem was about independent set and coloring. I introduced what is a vertex coloring, and I mentioned that chromatic number of the graph refers to the smallest number of colors that are required to properly vertex color the graph. When I say properly vertex color, I mean giving colors to the vertices in such a way that two non-adjacent vertices get different colors. Sorry, two adjacent vertices gets different colors, right. Whenever they are non-adjacent, they can get the same color, or they may get different color, it does not matter, we do not care, you can do it in any way. But whenever there is an edge between the two vertices, they should get different color, right. This is what, right, this is what we mean. So, the minimum number of colors required to do this thing is called the chromatic number. And now, the other concept we introduced was alpha of G, the cardinality of the maximum independent set, maximum independent set, independent set. So, this independent set meant that it is a collection of a subset of vertices, it is a subset of vertices of the graph, such that between any two vertices in this collection there is no edge, that means they are pairwise non-adjacent, right. And we wanted the maximum such collection, that was called maximum independent set. Cardinality is called the cardinality of the maximum independent set, and this has also got one name, another name, it is called a stability number, some others use that name. So, This is the notation used for this chi of g for the chromatic number, right. So, yesterday we told that when we consider the vertices as pigeons, there are n vertices, these are pigeons, then there are chi of g colors, right, chi of g colors. So, then each color is a set of vertices, each color refers to a set of vertices, namely the vertices which are colored by that particular color, and this is called the color class, right, color class. And the only observation we wanted was that if you consider one color class, the vertices inside that color class form an independent set. Why? Because if there was an edge between these two, then it is not possible to give the same color to both the vertices. No, that would be wrong, right. Then you will have to give different colors here. So, the fact that we have given same color to all of them means that forms an independent set. So, now each color forms a hall, that means colors forms the hall, right. The color classes are halls, pigeon halls here, and the pigeons are the vertices. Now, each vertex has to go to one of the pigeon halls, right, well, because in other words each vertex has to get one of the colors, and say so now the let us say number of colors is chi, right, and so we have to have, because number of colors is chi, because there are n vertices, it means that we should have n by chi number of pigeons in one of the halls, right, n by chi number of pigeons in one of the halls, right, is not it, because this is just the averaging argument. So, you have n pigeons, only chi classes here, right. So, for instance, yeah, this is, we know that, right. So, therefore, there should be at least right. For instance, if you take any number below this thing, that number into chi will be smaller than n will be greater than chi into any number which is, say, if I put -1 here into that, right. So, therefore, so the whichever integer is smaller than this thing, we can take the floor, right, floor. If it is already an integer, just take -1. If you take if it is not an integer, floor -1. So, n will be strictly greater than that. Therefore, our generalized pigeonhole principle says that, right, you should have this many at least this many pigeons going into one of the halls. This is what we get. So, therefore, we see that there exists one color class in which at least n by chi vertices have come. The point here is this n by chi need not be an integer. What we mean is, suppose it is an integer, we have at least that much. If it is not an integer, we have even, say, you can say seal of this thing, right. You can take the next integer, because the number of vertices is always an integer, right. So, this many will be there, that is what, right. So, it should be clear. For pictorially, this is what we mean. So, if this is G, so if I draw the color classes, though it is after giving the colors, I just collect the vertices of those color classes. So, let us see, so something like this, right. So, right. And so on. Right, these are, say, these are the colors, and now what we claimed was that, so one of the color classes should get at least because there are chi of them, these color classes, at least n by chi vertices, right. So, that is but then that each color class forms an independent set, right. So, this because therefore, the alpha of G, the maximum independent set has to be at least as much as this thing, that is what we get, right. Right. So, this is coming from the generalized pigeonhole principle. So, if you really wanted to see as if n greater than or equal to chi into some k, right, chi being the number of color classes, this is the number of pigeons, right, number of objects, chi is the number of classes into which we are dividing the object. If n is strictly greater than, suppose the number of object is strictly greater than chi into k, right, then we know that they should be one of the classes where k plus 1 objects have come, that is what we told. Here there is a little difficulty because these are this k we have to find out as an integer. So, what we do is, so suppose we will see whether it is n by k, chi is an integer. If n by chi is an integer, we can take it as n by chi, k as n by chi minus 1, right. Then we see that n by chi will come here. So, if n by chi was not an integer, we just take the floor here as k. So, that means we will get the, because n is strictly greater than that. So, therefore, yeah, we will get this from the generalized pigeonhole principle. This is what we did yesterday in the last class. And now the next question is again about graphs. Let G be an n vertex graph. If every vertex has a degree of at least n minus 1 by 2, then G is connected. So, here is again some notions which we have to explain. So, G and now every degree. So, we will say minimum degree of the graph is at least n minus 1 by 2, n being the number of vertices. N is the number of vertices, we can also write like this, n is the number of vertices. Suppose the minimum degree is at least n minus 1 by 2. So, what do you mean by minimum degree is at least n minus 1 by 2? That means every vertex has degree at least n minus 1 by 2. This again need not be an integer. If it is a fraction, we will have the seal of this, right, because the minimum degree cannot be a fraction. Now, we say that in this case G is connected. What do I mean by connected? Graph is connected if between any two vertices there is a path, right, there is a path. So, for instance, this is a connected graph, right, this is a connected graph, because if you want to go from here to here, you have a path here, right, you can reach from here without getting out of the graph from anywhere to anywhere. But on the other hand, if I introduce say this graph, the next graph, say if I say consider this graph, this is not connected. For instance, if I want to go from this vertex number 1 to vertex number 3, definitely I cannot, because I can go up to here, so I cannot reach here, right, it is not connected. This is the intuitive notion of connectivity. So, so this is a disconnected graph. So, we need only this much for this problem. We are claiming that suppose given a graph, and if every vertex has degree at least n minus 1, this problem will not come. So, there will be connectivity, that means there will be a path from each vertex to so each pair of vertices there will be a path, right. How will you show this thing? Now, suppose for contradiction, right, let us assume that it is not connected. That means you can find some two vertices, say x and y, such that they are not connected in that means there is no path in the graph from x to y. So, that means there is no edge between them, right. If there is a direct edge between them, then definitely they are connected, right, there is a path, there is a direct edge itself. So, it is like this. So, we do not have this, right, that is what we see. And now what about the remaining vertices? There are n minus 2 vertices here, because total n 1, 2 and n minus 2 left. And if I consider the degree of this thing, the neighbors of this thing, right, there are n minus 1 by 2 of them, right. I can only draw here because this vertex is not connected, this is not a neighbor of this thing. So, this is at least n minus 1 by 2, at least. And for this guy also we have at least n minus 1 by 2. Now, is it suppose if I have a common vertex here, that means this edge also is coming here, and say I can use another color, this edge also is coming here and this edge also is coming here, then definitely it is connected, because there is a path from here to here. Not only that, there is a path, there is a path of length 2, right. So, you can jump to here and jump to here. That means it should be such that this vertices, this I mean the vertices which are neighbors of this and the vertices which are neighbors of this thing, the vertices which are at the end of these red edges, like the way we have drawn earlier, the vertices at the end of these red edges and the vertices at the end of this green edges are to be disjoint. But we claim that by pigeonhole principle it is not possible. Why? Because there are, which are the pigeons here? Here these edges will be the pigeons, these edges will be the pigeons, here these edges, right. So, how many are there total? N minus 1 by 2 at least here and n minus 1 by 2 at least here. Total n minus 1 pigeons are here, these edges are the pigeons, right, this total red edges and the green edges. Now, the holes are these vertices, there are the vertices here, the vertices in this part, that is only n minus 2. So, there are n minus 2 holes and n minus 1 pigeons. So, the n minus 1 pigeons are trying to occupy these holes which are one less than that. Definitely the pigeonhole principle says that it is not possible to for each pigeon to go to a separate hole. You should have one hole means there should be one vertex here. So, let me draw this one vertex, right, such that two pigeons occupy that same hole, that means two of these edges come on that. But then it is not possible for two red edges to fall on the same vertex. So, that is the way we told that this is a simple graph, there is no multi edge, right. So, each of these edges starting from here has to go to different vertices. So, therefore, those two pigeons, one has to come from here and one has to come from here, that is the only possible way. So, it should be something like this. So, it is a contradiction to the fact that there was no connectivity in the graph. There is a path from this vertex to this vertex, two hop path. So, you can jump from here to here, right, in 2 hops, that is what we see, right. So, this shows that if every vertex has degree at least n minus 1 by 2, then the graph has to be connected, a simple application of pigeonhole principle into graph theory. Now, the next thing we will look is more interesting, say slightly more important theorem. It is one of the earliest theorems from extremal graph theory. It is called Mendels Theorem. If a graph G on 2n vertices contains n square plus 1 edges, then G contains a triangle. So, the question is like there is a graph G, right, it has 2n vertices. Now, we want to add as many edges to this 2n vertices, on this 2n vertices. We are talking about simple graphs only, such that so we do not want to make any triangle in the graph. Triangle means something like this, right, we do not want to create any triangle in this thing, right. How many edges, maximum how many edges can we put, right. For instance, if there are 2 vertices, you can just put one edge, fine. If there are 3 vertices, you can only put this much. So, 3 vertices, I am saying 2n vertices. 4 vertices we can put something like this, right. Any extra edge will create a triangle, right, any extra edge will create a triangle. So, there are 4 vertices. So, 4 means here, but if what we are claiming is if there are at least n square plus 1 edges, then we will create a triangle is what I say. Here this for 2n equal to 2, n was equal to 1, n square plus 1. So, this is not even possible to have n square plus 1 edges here. So, that is correct here. So, now for this one 2n is equal to 4, that means n equal to 2 here, right, 4 vertices. So, n square plus 1 means 2 square plus 1 5. So, you can put 4 edges without a triangle as you can see on 4 vertices, but if you put any more edge here, it forms a triangle, whichever way you try. Maybe you can try it like this till a triangle. There is no other way you can try it. So, what about 6 vertices? 6 vertices also you can try. So, 6 vertices we say n equal to 2n equal to 6, that means n equal to 3. So, n square plus 1 equal to 9 plus 1 is equal to 10. If you put 10 edges, you will definitely get a triangle is what it says, what this Mendels theorem says. So, up to 9 edges you can put, see for instance you can put, see yeah. So, we have it is okay, no triangle. So, we can connect it to here. So, now if we connect it to here or here, we are in trouble, right, because if you connect it to here, we will get a triangle connected to here. So, what about this? This you can connect to not this one you can connect, right, and then this one you can, this one you can connect to here, yes, and this one you can connect to not this okay, you already connected it, and here 3 plus 6 9 you have already put. Now, we are claiming that if you put one more edge, it will form a triangle, it looks like, right, if you try to put any edge. So, for instance, if you put any edge here, it is forming a triangle, right. So, this need not be the only way, you can try it in various possible ways. See, because I started with a cycle, maybe I did wrong initially, but you can always see that if there are 2n edges, you can put n square edges without 2n vertices, you can add 2n n square edges without creating a triangle. This is the way to do it. So, there are n vertices here on this side, n vertices, and you also put n vertices here on this side, right. There are total 2n vertices, and now add all the possible edges between this. Right. This is a bipartite graph, bipartite in the sense that the vertices are partitioned into 2 classes here. This is one part and this is one part and the other is this part, and within a part there is no edge. The edges are always from one part to the other. The edges are always from one part to the other. In that sense, it is a bipartite graph. So, you can remember the vertex coloring idea we talked in the last problem. So, if you try to color bipartite graph, you can easily see that you need only 2 colors. For instance, you can give the same color to every vertex on this side, because there is no edge between them, and a different color here on the other side, right. Just 2 colors are enough to color this thing. This kind of graphs are called bipartite graph. Now what I did is I connected every vertex on this side to the other side. So, n vertices here, n vertices, how many edges are there by the so called product rule, n into n, right, to n square edges have come here, n into n, n square edges have come here, right. So, n square edges, right. What is this product rule? I am counting the edges, I fix one of the endpoints here from this side, and then you can select the other endpoint as any from here. So, this is n, right, any from here, right. There are n possibilities. For the next one, there are again n possibilities. For the next one, there are again n possibilities. Therefore, n square possibilities to make edges, right. So, this is by so called product rule. So, therefore, there are n square edges here. Now, the point is we have not created any triangle. Why? Because, so suppose there is a triangle here. So, suppose this the triangle has to involve some vertex, right, say this is in that triangle, then follow that triangle. So, it goes to this side. So, now follow the next edge, because the next edge has to go to the other side back, right, because anyway that is the only way we have edges, right. Now, where will be the third edge? Third edge has to be here, but then we know that this edge is not present because it is a complete bipartite graph. It is a complete bipartite graph, complete because all the possible edges across we have put, right. So, this bipartiteness of this graph tells us that there is no triangle here. So, clearly, so we do not have any triangles in a bipartite graph, and we can get, so for instance, n vertex here, n vertex here, if you put n square edges you can get. The point the Mendels theorem makes is that if you have one more edge, then we will end up with a triangle. Here it is very obvious, because any extra edge if you have to put in one of these classes, and you are forming a triangle there now, because already all the cross edges are there. So, therefore, that like this, right, a triangle will come. But you need not work with bipartite graph initially, you can try in any way, but you cannot go beyond n square edges is what Mendels theorem. We want to show this thing. So, the simple trick is to use induction in conjunction with together with pigeonhole principle. So, what induction? Induction on n, because we are talking about 2n. So, we have seen that on 2 into 1, right, n equal to 1 case it is working, 2 into 2 on n equal to 4 vertices it is working, 2 into 3 6 vertices we have not verified, but we have seen some examples, but at least the first two cases we have n equal to 1 and 2 cases we have verified it. So, we can try induction. Let us assume that it works for n up to n. So, we want to do it for n plus 1. By the way, when I am talking about induction, again I am not formally explaining what induction is. Say I am not going to teach what induction is, because I think that it is it should be studied before 12th standard, right. Therefore, that is again I was mentioning initially that about numbers, certain things I will assume, like induction is one of those techniques which is very basic and which you should have studied by this time, and this course is above that, though I call it elementary, but not that elementary. So, induction n plus 1 we have to show. So, that means we will show that if there are n plus 1 square plus 1 edges in the graph on 2 into n plus 1 vertices, then there is a triangle is what we want. Up to now we know if there are n square plus 1 edges in a 2n vertex graph, then we have a triangle in the graph, you know. So, now it is, suppose this is not true, for contradiction let us say there are 2n there are 2n plus 1 vertices, 2n plus 2 vertices in the graph, that is 2 into n plus 1 vertices in the graph, and then we do have n plus 1 whole square plus 1, that is equal to n square plus 2n plus 1 plus 1 edges in the graph, and suppose there are no triangles, right. We will show that this is not correct, this cannot be true, right. How do we show? So, there are so many edges, we will pick up two vertices from the graph x and y which are connected to each other, right. See this is an edge here, right, two vertices x and y will pick up. Now, we remove x and y from the graph and look at the remaining graph, this is the remaining. So, because total 2n plus 1 2n plus 2 vertices were there. So, now 2 we have removed. So, here we have 2n vertices, right, in the remaining graph. So, now in these 2n vertices, see how many edges can be there. So, clearly if in this 2n vertices, in this induced subgraph on 2n vertices, when I say induced subgraph, I mean that the graph which is just formed by these vertices alone. We collect all the edges with both endpoints on these 2n vertices. We will discard, suppose there are some edges going out of this thing, we will discard all of them, right. This is the induced subgraph, right. Right. So, the induced subgraph on these 2n vertices can only have at most n square edges, right, n square edges here, right, 2n vertices and n square edges. Why? Because if we had n square plus 1 edges on these 2n vertices, then by induction hypothesis we do have a triangle in that, and that triangle is present in the bigger graph also, in this 2n plus 2 vertices also, but we know that it is not true. For contradiction we assume that such a triangle does not exist in this bigger graph. Well and good. Now, so we have n at most n square edges here, one edge I can see here. So, that one edge this right, this one edge, and yeah, this one edge, and here n square edge. So, the remaining is this 2n plus 1, remaining is this 2n plus 1. So, this 2n plus 1 edges should be where? Because we have not thrown away any edge from within this thing. I mean, if an edge at both endpoints in this 2n, inside this 2n like this, if an edge was like this, right, both endpoints inside this 2n vertices, then we have not removed it, and this we have already accounted by this last one. So, the remaining 2n plus 1 has to be across. So, I will use this red color. So, it should be coming from, it should be like this. So, the either it starts from x and reaches here, or it starts from y and reaches here, right, reaches into this 2n part, something like this, right. Now, these are 2n plus 1 of them, at least 2n plus 1 of them. Now, these are our pigeons, these are our pigeons, these red edges are our pigeons, and the holes are these 2n vertices. There are 2n vertices here in this part, right. This, say, this 2n, this within this 2n part there are this, within this we have 2n vertices, and these are the holes. Now, this 2n plus 1 pigeons are trying to occupy the holes, 2n holes. So, there should be one hole which at least 2 pigeons occupy. That means, 2 of these red edges should end up on the same vertex, right. This is a hole, the same vertex. So, 2 of these edges should end up on the same vertex. So, this is the situation here. So, there is this one vertex, then this is x, y, and then 2 edges are coming and sitting here. So, why do I draw it from one from x and one from y? Because it cannot be, both of them cannot be from y, right, because 2 different edges of y should end up in different vertices only. It is not possible for the 2 edges from y to occupy to come to the same vertex here. So, therefore, it should be one from x, one from y, that is important. And then you remember, here this edge was there, that means this edge was there, this edge was there, right. So, this forms a triangle now, right. Here this is forming a triangle. So, we have proved Mendels theorem. We have, what we have done is we have done induction on n, and we have used the pigeonhole principle very carefully here. So, this proves Mendels theorem. This is one of the earliest theorems in extremal graph theory. Like the kind of questions they ask is how big can a graph be if you want to make sure that it avoids a certain structure. Here triangle has to be avoided. The number of vertices is fixed. We are trying to see how big the number of edges can become, at the same time keeping the property that there are no triangles in the graph, right. So, this but anyway, we are not going to get into the details of extremal graph theory. So, we just mentioned it in passing. Now, we have done a few examples from graph theory. So, now we will look at some examples from geometry, some problems from geometry, simple examples. So, if 5 points are selected from the interior of an equilateral triangle, then 2 among them are such that the distance between them is less than half. So, once again, so this says, so you consider an equilateral triangle. Equilateral triangle means what? So, all the sides are equal, right, all the sides are equal. Now, you ask your friend to select as he pleases. So, no restriction, just that he has to select points, 5 points from the interior of the triangle. So, in this region, right, in this region he has to select here, in this interior of the triangle, not from the border, not from this edges of the triangle, in the inner part. 5 vertices he has to select, 5 points he has to select. Now, you ask him to select these 5 points such that they are all far apart. Far apart means the distance between any of them is at least any pair of them is at least half, means there are 5 points, any 2 you can select. So, between them if you measure the distance, it should be greater than equal to half. This is what we ask him. So, this is equilateral triangle is unit distance here. Now, this is not possible is what we are trying to say. He can try as much as possible, but as whatever he tries, it will not be possible to get 5 points like that. That is what we want to prove. Why is it so? Of course, if you had asked him to select 5 points from the equilateral triangle whose distance is more than 1, more than equal to 1, that would not be point. He can't even would not be possible. He can't even select 2 points like that, because within the equilateral triangle the distance is only 1. But now we are allowing him to keep the distance at least half. You can reduce the distance up to half, but you should not go below half. But still he cannot get more than 5 points is what we are claiming, right. So, let us see how it works, why it works, right. So, here suppose he selects any 5 points, he can draw 5 points, 2, 3, 5 points. The point is, suppose if you draw, so take the midpoint here, that means this distance is half and this distance is also half, and similarly the midpoint here, that this is half, this is half, and this is also half, right. And similarly the midpoint here, that means half distance here, and this is also half. And then connect these things. We can use a different color here. Yeah. Here we see 4 triangles, 1, 2, 3, 4. Now, the 5 points are selected. These 5 points are the pigeons for us now. So, now you can split these triangles into these points here, right, because interior points only. Up to here we will consider it as one hole, this one, and this one, this part we will consider as another hole. This is one hole, this is one hole including this maybe, and this is another hole, and then this one can be taken as another hole, and the remaining thing here can be taken as the 4th hole. There are 4 holes. I have marked it using different colors here, right. So, we have to put the borders into one of the, see, this border will go into this thing, this border will go into this thing, this border will go into this thing, this will not have any borders, this is just the interior of the, this inner triangle. Now, if you take 4 points, they should fall into these halls, right. That means these 5 pigeons are taking trying to occupy the 4 halls. There should be 2 of them which fall into the same hall, say here. Now it is very clear that it is again an equilateral triangle, half, 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 right equilateral triangle. So therefore you cannot, the distances cannot be smaller than half. The distances cannot be bigger than half, because these interior points only, they should be strictly smaller than half. That is what we have told, right. Right, because within an equilateral triangle. So now this is a simple pictorial, it is very pictorial. You can see the hall here as 4 equilateral triangles, and right. The pigeons are the 5 points and then they occupy it. Now the another question, another geometry question we want to consider is this. So 10 points are given within a square of unit size. Then we want to show that there are 2 of them that are closer to each other than 0.48 unit. Also there are 3 among them that can be covered by a disk of radius 0.5. How will you do this thing? So here we are talking about a square. I am not drawing it properly, of course. This is a square. So all distances are 1, 1, 1, 1. So unit square. Now I ask you to take 10 points. Ask your friend to take 10 points inside the square, inside interior of the square. Now we claim that however he tries, he cannot avoid 2 points becoming too close in the sense that they will become closer than 0.48 units. This is 1 unit. So this is 1 centimeter, then this 0.48 centimeter, right. It will become strictly less than 0.48 centimeter. Why is it so? The argument is like this. This time you cut this into 3 equal parts. So here 3 equal parts. Yeah, it will become like this. So we will get 9 equal squares here, and you see this is 1 by 3 each, right. This will be also 1 by 3. This distance is 1 by 3, this distance is 1 by 3. Similarly for each square, 1 by 3, 1 by 3. Now we have 10 points, these are the pigeons. We have 9 halls, you can see hall number 1, 2, 3, 4, 5, 6, 7, 8, 9. And these 10 pigeons occupy these 9 halls. So there should be one hall where 2 of the pigeons fall, say something like this, right. So the question is, this is a square of 1 by 3, 1 by 3. So here 1 by 3, 1 by 3. So if suppose assuming that these 2 pigeons fell into this, what will be their distance? Maximum distance is along the diagonal, as you can see, right. So I am not going for rigorous proofs here. So because the diagonal is the maximum distance within a square. So this is 1 by 3, this is 1 by 3, and then what is this? Pythagoras theorem tells us, so that is 1 by 3 square plus 1 by 3 square, root of this should be taken, that is root 2 divided by 3, which if you calculate you can see that something like 0.471 something like that will come, so which is strictly less than 0.48. that is all we meant, right. Okay. So therefore that is where the theorem comes, first statement comes. If you take 10 points, you cannot avoid 2 points coming too close. See, the 10 was selected because there are 9 things which you can see here. There is that is why we wanted the pigeons to be one more than the halls, right. So, for this argument to hold. Now, the second statement says that you can, if 10 points are selected, you can always find 3 points among them such that it can be covered with by a disk of radius 0.5. That means, if you draw a circle of radius 5 somewhere, 0.5 half somewhere, then you can capture 3 points from this thing. So, this is again like this, again that square. We first draw these 2 diagonals here for the square. Now, you can from elementary geometry you can see that. So, this I have not drawn it well, but these are all triangles here, right. These are all 4 triangles of equal size here. This diagonals are bisected by each other, that is a perpendicular this thing. So, diagonals are bisected by each other. Now, we consider each of these 4 triangles 1, 2, 3, 4 as holes. Now, you can use the generalized pigeonhole principle. 10 pigeons are there. This 10 is greater than say 4 into 2, 4 into 2, 8. So, therefore, there should be one hole which gets 3 pigeons, more than 2, one more than 2, 3 pigeons, right. So, let us say this hole gets that 3 pigeons. So, this hole gets that 3 pigeons, right. Now, we claim that whatever is inside this triangle can be enclosed by a circle of radius at most half. How will you do that? So, what you can do is you can find a circle of this triangle, that means a circle. Okay, so one has to draw it well. So, okay, I have not something like this. So, so that means circumcircle means each of these vertices, or this is this corners of the triangle are on the circle. This is called circumcircle. The triangle is inside this thing. Now, you see you can see that if you consider the center of the circumcircle comes over here, because here the distance is half, right, because this is also half. Suppose I take the midpoint of this thing, though the figure is not good at all, of course it should be something like this. Okay. So, okay. So, this is half, and then what would be this distance, and that should be, because this diagonal, say if you consider a square of unit length, and if you consider the diagonal, this is 1 1, this should be root 2, and if you consider the midpoint of it, this distance has to be root 2 by 2, that means 1 by root 2, right. Now, what should be this distance, right, if I take to the midpoint, if I drop something from here to the midpoint, I guess that is 1 by root 2 is, that means 1 by 2 is the square of 1 by root 2, and minus this is 1 by 2, that square is 1 by 4, you get 1 by 4. If you take the square root, it will become 1 by 2, right. So, this point will be the center of this circle. So, therefore, that radius of the circle itself is half, and then that means that this circle is actually capturing all of these 3 points, right. That circle is containing these 3 points. That means we have captured 3 of these points using a disk circle of radius half. That is what the other theorem stated. Again, as far as the pigeonhole principle, apart from the geometry which we use later, which you can work out, the pigeonhole part was only this thing. We have 10 points, that those are the pigeons, the holes are this thing. So, these triangles, there are 4 of them, therefore, we use the generalized pigeonhole principle to argue that there are 3 pigeons in one of the holes, and these, then we used a circle which can which is the circumcircle of this triangle, and we pointed out, we noted that the radius of that circle is only half. The next thing is a very famous thing. It is a statement about the sequences of distinct real numbers. And what does it say? It tells that suppose n square plus 1 distinct real numbers are there. N square plus 1 distinct real numbers, that means none of them are equal. Now, to try ordering these n square plus 1 numbers in any possible way, you can ask your friend to do that. So, n square plus numbers 1 numbers means how many possible ways you can do this thing. So, if you know about permutations, then there are n square plus 1 factorial ways of doing it, right. You can arrange in any way, n square plus 1 factorial ways. For instance, there were just 2 numbers a1, a2, a3. So, you could have put it in a3, a2, a1, or you could have put it as a3, a1, a2, or you could have put it as a1, a3, a2, and 2 more ways, right. A2, we can start with a2, a1, a3, and a2, a3, a1, 6 ways of doing it, right. That is the 3 factorial. 3 factorial is 3 into 2 into 1, right. This many ways of doing it. So, when you say factorial, why it is factorial? Because you can fill the first position in n square plus 1 ways, because there are so many of them. The second one in n square plus 1 minus 1, that is n square ways, and so on, right. So, by product order you can do it. So, now whichever ordering you take from this n square plus 1 factorial orderings. So, the next thing what you are interested in is to get certain people, certain subsequence from this thing, such that there is that is increasing or decreasing. So, you can visually say, suppose some n square plus 1 students are there in a class, and they are asked to go and stand on a queue. So, they stand on a queue like this, and assume that they all have different heights. Now, we can ask some people to step out, say this one to step out, this one to step out, So, how many n of them to step out? This is say x1, this is x2, this is x3. So, in this order x4, and the others will remain there. These people will just come to side of the queue, come out of the queue and stay here, and we can make sure that their heights are either in the increasing order or in the decreasing order. This is the statement, right. We will do the remaining in the next class. Thank you.